Some corners of the universe operate by a different set of rules entirely. We are going to explore why certain regions of space challenge our understanding of the known laws of physics. This is a journey into cosmic anomalies that are not science fiction, but documented scientific mysteries. By the end, you will see the cosmos through a completely new lens, appreciating the profound gaps in our current knowledge. How can galaxies spin faster than our models predict, and what unseen influence is guiding the expansion of the cosmos on the largest scales? What does it feel like to stand at the edge of a reality where our familiar physics reaches its limits? The universe runs on a set of instructions we thought we had finally decoded. For centuries, our understanding was built upon a few powerful pillars. Isaac Newton gave us the laws of motion and universal gravitation, a framework so elegant it could predict the path of a thrown ball or the orbit of a distant moon with stunning accuracy. It painted a picture of a clockwork cosmos where every action had an equal and opposite reaction, and gravity was a predictable, pulling force across empty space. Then Albert Einstein stepped in and turned that entire picture on its head. He proposed that space and time were not separate, rigid stages, but woven together into a single, flexible fabric called spacetime. Massive objects like stars and planets don't just pull on things, they actually warp this fabric, and what we feel as gravity is simply the motion of objects following the curves in this cosmic cloth. His theories also introduced a universal speed limit, the constant speed of light, a rule that nothing in the cosmos can break. Just as we were getting comfortable with this grand, cosmic scale, quantum mechanics revealed the surprising rules of the very small. Here, particles can be in multiple places at once, communicate across any distance through what we call entanglement, and their behavior is fundamentally a game of probability, not certainty. We've bundled these two monumental theories, relativity and quantum mechanics, into what scientists call the Standard Model. This model is arguably the most successful scientific theory in history, predicting everything from the existence of the Higgs boson to the precise timing of eclipses. It is the guidebook for our reality. But what happens when we take this guidebook to the most extreme environments the universe has to offer? We are about to discover that in the deepest voids and around the most massive objects, the pages of that book begin to blur, and the rules we rely on simply stop making sense. This discovery sent a shockwave through the scientific community. For decades, the prevailing assumption was that the universe, born from the Big Bang, was like a colossal event gradually running out of steam. The mutual gravitational pull of every galaxy, star, and speck of dust should have been acting as a cosmic brake, slowly decelerating the expansion over billions of years. The only real question was whether there was enough matter for this gravity to eventually pull everything back together in a great reversal, or if the universe would simply coast onward, forever expanding but at a steadily slowing pace. Then, in the late 1990s, two independent teams of astronomers made a measurement that reshaped this entire narrative. By observing incredibly distant and ancient stellar explosions, known as Type 1, a supernova, they were able to use them as cosmic mile markers. The light from these events revealed a truth far stranger than anyone had anticipated. The most distant galaxies, the ones we see as they were in the deep past, were moving away from us more slowly than our models predicted. But the closer, more recent galaxies were receding faster. This meant the expansion of the universe was not slowing down at all. It was speeding up. Imagine throwing a ball into the air, expecting it to slow, stop, and fall back to Earth, only to watch it shoot away from you faster and faster into the sky, defying gravity itself. That is precisely what the cosmos is doing on the grandest possible scale. This acceleration points to a mysterious, repulsive influence that overwhelms gravity across the vast emptiness of intergalactic space. Scientists gave this unknown element a name, dark energy. We cannot see it, we cannot detect it directly, but we can observe its profound effect, and the numbers are staggering. Dark energy is now calculated to make up about 68% of the entire energy content of the universe. Think about that for a moment. The material we understand, all the galaxies, planets, stars, and gas, everything we can see and touch, accounts for less than 5% of the cosmos. The rest is this unseen sector with dark energy as its dominant, enigmatic force. Its nature is perhaps the greatest question in modern physics. Is it simply a property of empty space itself, what Einstein once called the cosmological constant, a steady pressure woven into the fabric of the universe? Or is it something more dynamic and evolving, a field that physicists call quintessence, which could change over time? Whatever it is, dark energy is not just a minor puzzle. It is actively shaping the ultimate fate of the entire cosmos, inviting us to consider a humbling possibility. Our most cherished laws of physics, forged in the relative calm of our local galactic neighborhood, might be entirely incomplete when applied to the universe as a whole. This acceleration driven by dark energy is not the only ghost in the cosmic machine. While dark energy pushes the universe apart on the largest scales, a second, equally profound anomaly reveals itself when we look closer, within the majestic swirl of individual galaxies. Our own Milky Way offers a perfect example. Picture a star orbiting the galactic center, far out in one of the spiral arms. According to the laws of gravity established by Newton and refined by Einstein, the speed of that star should be dictated by the gravitational pull of all the mass inside its orbit, primarily the brilliant core of stars at the galaxy's heart. We can calculate that pull based on the light we see, expecting stars on the outskirts to orbit much more slowly, just as Pluto in our own solar system moves far more sluggishly around the Sun than Mercury does. But when astronomers actually measured these stellar speeds, they found something completely baffling. The stars in the outer regions of galaxies are not moving slowly at all. They are racing around at velocities so high that the gravity from all the visible matter, the stars and gas we can observe, should be utterly incapable of holding them in place. At such speeds, these stars should have been flung off into the blackness of intergalactic space long ago, like marbles spun off a plate that is turning too fast. Yet the galaxies remain intact. This glaring mismatch between prediction and reality, shown on graphs called rotation curves, presents an inescapable conclusion. There must be a tremendous amount of mass that we cannot see, a form of matter that does not emit, absorb, or reflect any light, enveloping each galaxy in a massive, invisible halo. Its gravitational grip is the only thing keeping those high-speed stars from flying away. Scientists call this mysterious substance dark matter. Its influence is not a small correction, it is a dominant force. When we add up the cosmic budget, dark matter makes up about 27% of the universe, outweighing all the normal matter, every star and planet, by a factor of more than 5-to-1. This unseen matter acts as a cosmic scaffold, a hidden framework whose gravity guided the formation of the first galaxies and now holds them together. The hunt to identify what dark matter actually is represents one of the most intense efforts in modern science. It cannot be any particle we currently know. Neutrinos are too light and fast. Black holes of the required abundance would disrupt star clusters in ways we do not observe. So physicists are searching for hypothetical new particles, entities like weakly interacting massive particles, or WIMP, which would barely interact with normal matter except through gravity. Another candidate is the action, a theoretical particle that is incredibly light but could exist in vast numbers. Decades of sophisticated experiments, deep underground and powerful particle colliders have so far come up empty, failing to directly detect a single dark matter particle. This persistent silence forces us to confront a radical possibility. Perhaps the mystery of the galactic rotation curves is not pointing to unseen matter, but to a flaw in our understanding of gravity itself. Could the laws we use, which work so perfectly in our solar system, break down on the immense scale of a galaxy? This is the core of the conflict, a fundamental gap in our knowledge that asks whether we are missing a major part of the universe's contents, or whether we need to rewrite the rules of the cosmic game entirely. The conflict between dark matter and modified gravity is a profound puzzle, but it is not the only place where our cosmic rulebook fails. There exists an even more absolute boundary where the known laws of physics are not just challenged but are utterly erased. This is the event horizon of a black hole. Think of it as the ultimate point of no return, a one-way cosmic doorway from which nothing, not even a single particle of light, can ever come back. It is not a physical surface you could touch, but a mathematical threshold in space where the black hole's gravitational pull becomes so overwhelmingly powerful that the escape velocity exceeds the speed of light. Since nothing in the universe can travel faster than light, crossing this boundary means vanishing from our observable reality forever. General relativity provides a stunningly accurate description of the gravity that creates this boundary, but when it tries to describe what happens to matter that falls inward, its equations reach a profound conclusion. The theory suggests that all the material collapsing into a black hole is drawn toward an infinitely small, infinitely dense point at the very center, a concept known as a singularity. At this point, the curvature of spacetime itself becomes infinite, and the very tools we use to describe the cosmos, the fabric of Einstein's equations, simply break down and yield nonsensical answers. It is a place where the laws of physics as we know them cease to have any meaning. This sets up a direct confrontation with another pillar of modern physics, quantum mechanics. A fundamental quantum law states that information, the unique identity of every particle, can never be truly destroyed. It can be scrambled and rearranged, but it must, in principle, be recoverable. So, what happens to all the information about a star, a planet, or a book that falls into a black hole? Does it vanish at the singularity, erased from the universe for good? This is the heart of the black hole information paradox, a fundamental conflict that has puzzled physicists for decades. It suggests that our two most powerful theories, general relativity and quantum mechanics, cannot both be completely correct when they meet at this extreme edge. For a long time, these ideas were purely theoretical, but recently we have been granted our first direct glimpses of these cosmic phenomena. The Event Horizon Telescope, a global network of observatories acting as a single Earth-sized dish, captured the now iconic image of the supermassive black hole at the heart of the galaxy Messier 87. That glowing ring of light is not the event horizon itself, but the shadow it casts against the swirling, superheated matter that is about to fall in. This monumental achievement provided the first direct visual evidence that event horizons are real, physical structures in the universe, just as Einstein's theory predicted. Yet, the interior of a black hole remains the ultimate locked room mystery. We can never receive a signal from inside, and so its secrets are hidden from direct observation. This forces theoretical physics to push into uncharted territory. The event horizon is the very place where the smooth, continuous fabric of spacetime described by general relativity must somehow merge with the fuzzy, probabilistic grain of the quantum world. To resolve the paradoxes and understand what truly happens at this boundary, we need a new, unified theory, one that can seamlessly blend gravity with quantum mechanics. This quest for a theory of quantum gravity is not just an academic exercise, it is a journey to the very limits of human understanding, where the next revolution in physics is waiting to be born. Deep within the black hole's powerful embrace, the ultimate cosmic anomaly awaits. General relativity points to a final destination for all the matter and energy that crosses the event horizon, a point of extreme density and curvature known as a singularity. Here, the very concepts of space and time as we understand them lose all meaning. The equations of our most successful theory of gravity produce results that are not just strange, but physically nonsensical, signaling a complete breakdown of our scientific framework. Infinities do not appear in the natural world. They are the universe's way of telling us that our map has a fundamental tear in it. We have reached the edge of the known. Fortunately, this paradoxical point is locked away from our view, shielded by the event horizon. This cosmic censorship protects the outside universe from the unpredictable conditions within, but its theoretical existence presents an intellectual crisis. It forces us to admit that our understanding of reality is fundamentally incomplete. To resolve this, physicists are turning to speculative but promising theories of quantum gravity. String theory, for instance, suggests that the core of a black hole may not be a singularity at all, but a tangled, vibrating ball of fundamental strings called a fuzzball, a finite, though still incredibly dense object. Another idea from loop quantum gravity proposes a quantum bounce, where matter is not crushed to an infinite point, but reaches a maximum density and rebounds, potentially giving birth to a new universe in a process far removed from the sterile singularity. Unlocking the true nature of a black hole's heart is more than an academic pursuit. It is the essential next step toward a unified theory of physics, one that could finally reveal the principles that govern reality under the most extreme conditions imaginable. This repulsive force woven into the cosmos is the very opposite of gravity's pull. While gravity draws matter together, dark energy acts as a cosmic pressure, pushing the fabric of space itself apart. Einstein's own equations for general relativity contained a seed of this idea, a term he called the cosmological constant. He originally introduced it as a kind of mathematical adjustment to achieve a static universe, a notion he later set aside when the expansion of the universe was discovered. Yet, with the revelation of cosmic acceleration, the cosmological constant has made a dramatic return. It represents a simple, elegant solution, the idea that empty space itself possesses a fundamental, unchangeable energy density that exerts a negative pressure, driving galaxies away from one another. This concept fits the observational data remarkably well, but it introduces one of the most profound challenges in all of theoretical physics. When we try to calculate the expected energy of empty space using our best theory of the small-scale quantum world, the value we get is vastly different from what we observe. The predicted energy is a number with 120 zeros after it, far larger than the measured value. That is not a small rounding error. It is the greatest mismatch between theory and experiment in the entire history of science. It is as if we calculated the weight of a single grain of sand and our theory gave us the mass of an entire galaxy. This cosmological constant problem suggests we are fundamentally misunderstanding the nature of nothingness itself. In response, some physicists propose a more dynamic alternative known as quintessence. Imagine this not as a fixed property of space, but as a kind of invisible, cosmic fluid that permeates the universe. This fluid's properties could change over time, its repulsive strength shifting across the eons. While this offers a potential way to avoid the staggering numbers of the cosmological constant problem, no observational evidence has yet confirmed that dark energy is anything other than a constant force. The ultimate effect, however, is undeniable. On the grandest scales, where the average density of matter is incredibly low, the subtle push of dark energy accumulates into an unstoppable tide. It overwhelms the gentle pull of gravity between distant galaxy clusters, forcing them to recede from each other at a rate that grows faster with every passing moment. This steady acceleration does more than just reshape our map of the cosmos. It writes its final chapter. If dark energy remains constant, as the cosmological constant suggests, the future it paints is one of growing isolation and fading light. Galaxies beyond our own local group will eventually be carried away so quickly that their light will no longer be able to reach us. The observable universe will contract, and the cosmos will become a far colder, darker, and more solitary place over trillions of years. The nature of this repulsive force, whether it is a fixed feature of space or an evolving field, holds the key to the ultimate fate of everything. To unlock it, we must confront the profound question of why the energy of nothing is not, in fact, nothing at all. Even as dark energy pushes the cosmos apart on the grandest scale, a different kind of mystery weaves the universe together on the smallest. Deep within the quantum realm, particles can become linked in a way that utterly defies our classical understanding of space. Two particles born from the same event can become entangled, their identities forever intertwined. Their properties, like direction of spin, are not decided until the very moment one is measured. And in that instant, its distant partner, no matter how far away, adopts a corresponding state. This connection appears to be instantaneous, acting across any distance without any detectable signal or force carrier traveling between them. It is as if you had a pair of magical coins, one given to a friend who then traveled to a distant star. The moment you flip your coin and see it land on heads, you know with absolute certainty that your friend's coin, light years away, has landed on tails. This phenomenon, called quantum non-locality, seems to directly challenge the cosmic speed limit set by relativity, the rule that nothing can travel faster than light. Yet countless experiments have confirmed this is exactly how our universe works, with entanglement demonstrated over distances of hundreds of kilometers. The crucial distinction is that while the correlation is immediate, no usable information, no message can be sent this way. You cannot force your coin to land on a chosen side to send a signal. You can only observe the random outcome and know what your friend must see. This is not a loophole for faster-than-light communication, but a profound clue about the nature of reality itself. It suggests that the universe is fundamentally interconnected in a way that makes a mockery of distance. The vast emptiness of space separating two entangled particles might not be the fundamental stage we imagine it to be, but rather an emergent property, a surface illusion. This quantum behavior forces a direct confrontation with the worldview of general relativity, which is built on the principle of locality, the idea that objects are only influenced by their immediate surroundings and that signals take time to travel. Entanglement reveals a deeper layer of reality where separation is, in a sense, an illusion. The quest to build a single theory that can house both the smooth, geometric fabric of spacetime and the interconnected web of the quantum world is the great unsolved problem of modern physics. It asks us to consider that the true architecture of the cosmos might be something far stranger and more deeply unified than we have ever dared to imagine. The seamless fabric of the cosmos presents us with another profound riddle, one etched into the oldest light we can see. When we map the faint afterglow of the Big Bang, the cosmic microwave background, we find a universe of almost perfect equilibrium. From one distant horizon to the other, the temperature is uniform to within a fraction of a degree. This seems logical at first glance, until you realize that those regions on opposite sides of the sky have never had time to exchange heat or information. The universe was simply not old enough for light or any influence to have traveled between them to even out their temperature. According to the standard Big Bang timeline, these areas should be as disconnected as two islands that have never known of each other's existence, each with its own unique climate. Yet they share an identical temperature, as if they were once part of the same, intimately connected room. This is the Horizon Problem, a cosmic conundrum that challenges the very foundation of our origin story. How can the universe be so uniform if its parts were never in touch? The most widely accepted solution is a dramatic revision of the universe's first moments, a theory known as cosmic inflation. It proposes that a split second after its birth, the universe underwent a growth spurt of unimaginable scale. For a fleeting fraction of a second, space itself expanded faster than the speed of light, inflating a subatomic speck of space into a volume larger than our entire observable cosmos. This incredible stretch took a tiny, homogeneous patch that was already in thermal contact and blew it up to become everything we can see today. The distant regions that now appear causally disconnected were once neighbors, close enough to share their temperature before being separated by this rapid expansion. While inflation elegantly solves the horizon problem, it introduces its own profound mystery. What could possibly power such an extreme event? Physicists propose the existence of a hypothetical field, dubbed the inflaton field, which permeated the early universe. This field would have possessed a peculiar kind of energy, acting like a form of anti-gravity that forced space to expand at an exponential rate. Then, just as suddenly as it began, this field would have transformed, converting its immense energy into the hot soup of particles that would eventually form galaxies and stars. The mechanism is elegant, but the inflaton field itself remains entirely speculative, its true nature one of cosmology's great unsolved puzzles. This has led some scientists to consider even more radical alternatives, such as bouncing cosmologies where the Big Bang was not a true beginning, but a transition from a previous phase of the universe. Whether through inflation or a cosmic bounce, the Horizon Problem stands as a powerful reminder. Our standard model of the cosmos, for all its successes, is likely just a close approximation of a much deeper and far more mysterious reality. Our very existence hinges on a cosmic oversight. Every star, every planet, and every one of us is made of matter. But the laws of physics, as we currently understand them, present us with a startling paradox. The Big Bang should have created a perfectly balanced universe, with matter and its mysterious twin, antimatter, born in absolutely equal amounts. For every particle of matter, there should have been an antimatter counterpart. The problem is, when a matter particle meets its antimatter twin, they do not simply coexist. They transform into pure energy, leaving nothing behind. If the early universe had been perfectly symmetrical, all of its contents should have mutually transformed, leaving a vast, empty cosmos filled with nothing but fading radiation. There should be no galaxies, no solar systems, and certainly no one here to ponder their absence. The fact that we are here, in a universe brimming with galaxies made of matter, means that this perfect symmetry was broken. Somewhere in the first fleeting moments, a fundamental rule was bent, allowing one single, solitary particle of matter to survive for every billion matter-antimatter pairs that transformed. That tiny 1 in a billion imbalance is all that we are made of. The entire observable universe is the enduring remnant from that near-total transformation. So what caused this great cosmic favoritism? Physicists point to a necessary ingredient known as charge parity violation. In simple terms, this means that the laws of nature must treat matter and antimatter slightly differently. We have actually observed this in the decay of certain exotic particles, like kaons and B mesons, where matter behaves just a fraction of a percent differently than antimatter. But here is the catch. The amount of asymmetry we have measured in our most powerful particle colliders is far too small to account for the overwhelming dominance of matter we see in the cosmos today. It is like finding a single dropped coin on the street and trying to explain the existence of all the world's treasuries. The standard model of particle physics, for all its precision, cannot produce the level of imbalance required for our universe to exist. This forces us to look beyond to theories that introduce new particles or new forces active only in the universe's earliest moments. One compelling idea is leptogenesis, which suggests that ultra-heavy, sterile neutrinos decayed in the early universe, and in doing so, violated charge parity symmetry on a grand scale, ultimately generating the excess of matter we see today. Another path is electroweak baryogenesis, which looks for the necessary conditions during a pivotal phase transition in the cosmos's first moments. Yet, for now, these remain elegant ideas on paper, awaiting experimental confirmation. The baryon asymmetry problem is not a minor curiosity. It is a fundamental challenge to our understanding of nature's most basic rules, a quiet testament that the deepest workings of reality hold a subtle preference, a gentle leaning that made our material world and our very lives possible against all odds. The predictable clockwork of the cosmos faced a subtle but persistent challenge from two robotic explorers drifting toward the stars. For decades after their launch in the 1970s, the Pioneer 10 and Pioneer 11 spacecraft transmitted a steady stream of data back to Earth as they journeyed beyond the outer planets. Yet, hidden within their precise navigation signals was a tiny, stubborn mystery. Both probes were experiencing a minuscule, unexplained deceleration, a constant sunward tug equivalent to just 1/10,000,000th of the gravity we feel on Earth. This was the Pioneer anomaly, a whisper of a force that should not have been there. It was as if these spacecraft, on their long journey into the void, were driving with an almost imperceptible brake applied, a phantom hand gently slowing their escape. For years, this unusual behavior fueled speculation about new physics. Could it be evidence of a modification to Einstein's theory of gravity in the weak field regime of the outer solar system? Was it a sign of unseen matter, a local haze of dark matter subtly altering the gravitational landscape? The possibility was electrifying, suggesting our most trusted laws might fray at the edges of our own celestial neighborhood. The ultimate resolution, however, came not from rewriting physics textbooks, but from meticulous detective work. Scientists constructed the most detailed thermal model of the aging spacecraft ever attempted. They realized that the plutonium in their power sources was constantly generating heat, which was radiated away from the spacecraft's surfaces. This thermal radiation, while incredibly faint, carried momentum. It was acting like a gentle but constant breeze, blowing against the direction of travel and providing just enough pressure to create the observed deceleration. The primary cause of the anomaly was not a new force of nature, but the simple, overlooked physics of heat. Yet, even after accounting for this thermal recoil, some researchers point to a tiny residual effect that remains unmodeled. This serves as a powerful lesson in cosmic humility. Similar unmodeled nudges have been detected in the trajectories of other distant spacecraft, each a potential clue. Are these discrepancies merely the result of other subtle engineering effects we have yet to fully characterize, or could they still be faint signatures of something more profound? These minute deviations remind us that our mastery of gravity and motion, while incredibly precise, is not yet perfect. The deep space between the planets is not an empty stage, but a complex environment where every watt of power and every patch of warmth on a spacecraft's hull must be accounted for. The relentless pursuit of these tiny anomalies drives incredible improvements in our navigation and design, forcing us to become better, more careful observers of our own creations. And in that final sliver of uncertainty, a door is left open, a possibility that the outer reaches of our solar system may still hold subtle secrets about the fundamental nature of gravity itself. Even the most precisely calculated cosmic maneuvers can reveal a hidden whisper of the unknown. While the pioneer anomaly was ultimately traced to the gentle push of thermal radiation, another mystery emerged much closer to home, in the delicate gravitational dance between a spacecraft and our own planet. This is the flyby anomaly, a subtle but persistent riddle hidden within one of space exploration's most trusted techniques, the gravitational slingshot. To gain speed for their long journeys to the outer planets, spacecraft often swing closely past Earth, using our planet's gravity like a whip to fling them onward. Their trajectories are plotted with incredible precision, down to the millimeter per second. Yet, for a handful of these missions, something peculiar happened. As the spacecraft, like Galileo and near-Earth asteroid Rendezvous, raced away from Earth, radio tracking revealed a tiny, unexplained boost in their velocity. The change was minuscule, just a few millimeters per second, a difference smaller than a snail's pace over an entire year. On its own, such a tiny deviation could be dismissed as a tracking glitch or an unmodeled puff of solar wind. But the fact that similar, unexplained speed changes appeared across several different flybys turned a possible error into a compelling puzzle. What could be giving these spacecraft an unexpected, extra nudge? The immediate suspicion fell upon our own planet's complex gravitational field. Perhaps the models of Earth's slightly lumpy gravity, shaped by dense rock and deep ocean trenches, were not quite perfect. Or maybe the planet's rotation was imparting a subtle, uncalculated effect through a phenomenon known as frame dragging, where a massive spinning object like Earth very gently twists the fabric of spacetime around it, like a spoon stirring a thick liquid. If our maps of Earth's own gravity were incomplete, that could account for the anomaly. Yet other proposals reached for more exotic explanations. Could it be a hint of some new, very weak long-range force that only becomes noticeable during these high-speed, close encounters? Or does it point to a slight modification in our understanding of inertia itself, the fundamental property that governs how objects respond to forces? For a time, the flyby anomaly presented a real possibility that new physics was hiding in plain sight, etched into the paths of our robotic explorers. The story, however, has evolved with painstaking analysis, as our measurements of Earth's geoid, the planet's true gravitational shape, have become exquisitely detailed thanks to missions like the Gravity Recovery and Climate Experiment. Many of the anomalous flyby readings have been reconciled. It appears that the primary source was our own imperfect knowledge of the very gravity well we were using as a slingshot, better accounting for the planet's complex mass distribution and rotational dynamics seems to explain most of the discrepancy. But the case is not entirely closed. A faint whisper of the anomaly may remain in the data for certain flybys, a quiet signal that continues to intrigue a handful of researchers. The true legacy of the flyby anomaly is not necessarily a rewrite of physics, but a powerful lesson in humility and precision. It reminds us that our cosmic map, even of our own home, still contains uncharted subtleties. These tiny discrepancies force engineers and scientists to become celestial detectives, accounting for every conceivable influence, from the pressure of sunlight to the faint drag of Earth's outer atmosphere. In the relentless pursuit of these millimeters per second, We are driven to observe our world and the laws that govern motion with ever greater clarity, ensuring that the next time an anomaly appears, we will be ready to hear its true message. Even the oldest light in the universe seems to whisper of a hidden structure. Etched across the entire sky is the cosmic microwave background, the faint afterglow of the Big Bang, and for decades it has been our ultimate proof of a cosmos that is largely uniform. The standard model of cosmology rests upon this foundational idea of isotropy, the principle that the universe on the largest scales has no preferred direction and looks the same in every way no matter where you are. But when scientists created the most detailed maps ever of this primordial light, using data from the Planck satellite, they noticed something deeply unexpected. The subtle temperature fluctuations, the hot and cold spots that are the seeds of all future galaxies, are not scattered randomly as our theories predict. Instead, they appear to be aligned along a particular cosmic axis, a mysterious preferred direction that has been nicknamed, with a hint of dramatic irony, the axis of evil. This is not a small statistical fluke. It is a large-scale correlation that seems to challenge the cosmological principle itself. It is as if you walked into a vast, endless forest expecting the trees to be pointing in every possible direction, only to find that all of them are subtly leaning toward the same, unknown point on the horizon. What could possibly cause the universe to remember a direction from its very birth? The immediate thought, of course, is that we are being misled. Perhaps the signal is influenced by foreground light from our own Milky Way galaxy, a cosmic smudge on the lens of our telescopes. Or maybe there is a subtle, unaccounted-for systematic error in how the data was processed. Yet, even after painstaking efforts to remove these potential influences, the strange alignment remains. This has encouraged cosmologists to consider more profound possibilities. Could the shape of space itself be different than we think? Some models of cosmic topology suggest that space might be finite and connected in a complex way, like a hall of mirrors, creating the illusion of patterns across the sky. Others look to the era before the Big Bang, to speculative ideas like a preceding cosmic phase whose imprints were frozen into the newborn universe. Each potential explanation challenges the clean, simple story we have told ourselves about cosmic evolution. The axis of evil serves as a profound and humbling reminder. Our entire understanding of the cosmos is built upon a set of elegant assumptions, and when the universe presents us with a pattern that questions those assumptions, we are invited to listen. It is a quiet but persistent signal that the true history of everything may be far richer and far more strange than our standard model allows. Even the most energetic particles in the universe face a cosmic speed limit. From the depths of space, atomic nuclei traveling at nearly the speed of light, known as ultra-high energy cosmic rays, constantly reach our atmosphere. These are not mere specks of dust. They carry more energy than a professionally thrown baseball, all compressed into a single subatomic particle. According to a prediction made by physicists Greisen, Zatsepin, and Kuzmin, there should be a strict upper boundary to this energy, a point now called the GZK Cutoff. Their reasoning was based on a simple, inevitable interaction. As these ultra-high energy protons travel across millions of light years, they should constantly meet the faint, leftover photons of the cosmic microwave background, the pervasive afterglow of the Big Bang that fills all of space. Each encounter would take a little of the proton's energy, like a marathon runner constantly moving through a dense, invisible fog. Over intergalactic distances, this process should slow even the most powerful cosmic rays, ensuring that none with energies beyond a certain threshold could ever reach Earth. It was a beautiful, self-enforcing rule written into the fabric of the cosmos. But the universe, it seems, had other plans. Giant observatories like the Pierre-Auger Array, with its thousands of square kilometers of detectors, have repeatedly recorded cosmic rays that move right through this theoretical ceiling. These particles arrive with energies that, according to our best models, they should have lost long before completing their journey to our planet. It is as if that marathon runner not only finished the race, but arrived at the finish line moving faster than when they started. This presents a deep puzzle. Are our models of how particles lose energy across vast distances somehow incomplete, missing a key piece of physics that allows these cosmic rays to travel undisturbed? Or is the answer even more straightforward, suggesting that these ultra-high energy particles are not coming from distant, ancient galaxies at all, but from surprisingly nearby sources? If they originate within our own local cosmic neighborhood, perhaps within a few 100 million light-years, they would not have had enough time or distance to be slowed by the microwave background fog. This has triggered a search for local astrophysical accelerators of unimaginable power. Could the massive black holes at the centers of active galaxies be sending these particles like a cosmic signal? Or are we witnessing the transformation of exotic, theoretical relics from the early universe, particles so massive and rare that their change releases these incredible bursts of energy? The GZK cutoff question is more than a technical difference. It is a direct challenge at the intersection of the very large and the very small. It brings particle physics and cosmology to meet each other, asking whether we fully understand the rules for the most energetic events since the birth of the cosmos. Each detection of a super-cosmic ray is a message from the extreme universe, a single data point that carries the potential to reshape our understanding of fundamental forces and the unseen pathways that connect the farthest reaches of space to our own world. Even our most precise cosmic measurements are now locked in a quiet but growing disagreement. This conflict centers on a single, fundamental number, the Hubble constant, which describes how fast the universe is expanding today. For decades, astronomers have pursued this value using two powerful but very different methods. The first looks back to the universe's infancy, to the pristine snapshot of the cosmic microwave background. By analyzing the subtle patterns in this ancient light, scientists can run the cosmic film backward, calculating how the universe must have evolved to reach its present state, including a predicted value for the expansion rate. The second method is more direct, observing relatively nearby stars and supernova to build a cosmic distance ladder, measuring how quickly galaxies are receding from us right now. In a perfectly understood cosmos, these two approaches should arrive at the same answer. They do not. The early universe method suggests a slower, more sedate expansion, while local measurements consistently return a faster, more hurried rate. The gap between them is not shrinking with better data, it is widening into a stubborn discrepancy now known as the Hubble Tension. This is not a small statistical error, it is a direct challenge to the standard model of cosmology. It is as if you calculated how fast a tree should be growing based on the size of its seed and the nutrients in the soil, only to go outside and find it is already twice as tall as your model predicted. Something in our cosmic story is missing. The immediate thought turns to our instruments. Could there be hidden, unknown errors in how we calibrate the cosmic distance ladder, perhaps in our understanding of the Cepheid variable stars we use as standard candles? Or are we misinterpreting the complex physics of the early universe encoded in the microwave background? Yet, after years of careful review, no single systematic error has been found large enough to bridge the divide. This persistence leads cosmologists to consider more profound possibilities. Perhaps dark energy is not the constant force we assume it to be, but a dynamic entity that has grown stronger or weaker over cosmic time, subtly altering the expansion history. Or maybe the early universe contained an additional, fleeting type of radiation or a new type of neutrino that left a unique fingerprint on its evolution. Some ideas even suggest a brief, early episode of modified gravity that changed how structures first formed. Each potential solution requires adjusting the standard model in a fundamental way. The Hubble tension is more than a technical disagreement between datasets. It is a direct probe into the completeness of our cosmic model. Resolving it is not just about finding the right number. It is about discovering which chapter of our cosmic story we have misread, and what new physics is waiting to be written into the margins of our map of the universe. The quietest place in the universe is not truly empty. According to quantum field theory, the vacuum of space itself is a seething, turbulent sea of energy. At the very smallest scales, virtual particles flicker in and out of existence, borrowing energy from the void for fleeting moments before vanishing again. This ceaseless activity, known as zero-point energy, means there is no such thing as a true void, only a vibrant, energetic substrate underlying all of reality. This quantum jitter should contribute an immense energy density to empty space, a pressure that should have a dramatic gravitational effect, powerfully warping the fabric of spacetime. When physicists calculate the expected strength of this vacuum energy, the number they arrive at is so colossal it defies comprehension, a value with 120 zeros after it. This prediction stands in stark, almost absurd contrast to the value we actually observe. Measurements of the cosmic expansion rate driven by dark energy tell us that the vacuum energy is there, but its value is almost zero, a number smaller than the prediction by a factor of 10 to the power of 120. This is not a small error. It is the largest discrepancy between theory and observation in the entire history of science. Scientists call this the vacuum catastrophe, a name that perfectly captures the sheer scale of the theoretical challenge. It means our two most powerful theories, quantum mechanics and general relativity, are giving us answers about the most basic property of space, its inherent energy, that are impossibly, profoundly different. The gravitational effect of the predicted zero-point energy should curve the universe into a microscopic knot, yet we observe a cosmos that is vast and flat. How can this be? One proposed solution lies in the elegant mathematics of supersymmetry, a theoretical framework that suggests every known particle has a massive, unseen superpartner. If these superpartners existed, the frenetic energy of their quantum fluctuations could perfectly cancel out the contributions from ordinary particles, leaving a net energy of nearly zero. The challenge is that no evidence for these supersymmetric particles has been found in our most powerful particle colliders. Another, more philosophical answer comes from the concept of the multiverse. In an infinite landscape of parallel universes, each with its own random value for the vacuum energy, we naturally find ourselves in one of the rare, hospitable bubbles where the value is small enough to allow galaxies and life to form. This anthropic reasoning offers an explanation, but for many, it feels like a step back from the goal of a predictive, fundamental theory. A third possibility is that we are simply wrong about how vacuum energy gravitates. Perhaps the frantic activity of the quantum world does not couple to gravity in the way that normal matter and energy do, meaning the spacetime we experience remains smooth and flat despite the underlying turmoil. The vacuum catastrophe is more than a mathematical inconvenience. It is a direct signal that we are missing a crucial piece of the puzzle that connects the quantum realm to the cosmos. Resolving it is not just about fixing a number, it is about discovering the true nature of nothingness itself, and in doing so, taking the next essential step toward a theory that can finally describe all of reality, from the smallest whisper of a virtual particle to the grand expanse of the accelerating universe. Our cosmic recipe book, written in the aftermath of the Big Bang, has a single, stubborn typo. In the universe's first 20 minutes, a process known as Big Bang nucleosynthesis forged the lightest elements from a searing primordial soup. The calculations for how much hydrogen, helium, and lithium should have been created are exquisitely precise, and for the most part, they are a spectacular success. The observed abundances of hydrogen and helium throughout the cosmos match the theoretical predictions almost perfectly, a cornerstone proof of the Big Bang theory itself. But then there is lithium. The simplest form, lithium-7, presents a glaring problem. The oldest stars in our galaxy, which formed from nearly pristine material and should preserve the original chemical signature of the cosmos, contain only about 1/3 of the lithium that our models insist should be there. It is as if you followed a cherished family recipe to the letter, and every time you baked the cake, one key ingredient was consistently and mysteriously absent. This is the lithium problem, a quiet but profound anomaly that has resisted explanation for decades. Where did all the lithium go? One possibility is that our understanding of the nuclear physics in that first frantic hour is subtly flawed. Perhaps a key nuclear reaction, one that creates or removes lithium, has a slightly different probability or cross-section than we have measured in our laboratories. A tiny adjustment to one of these numbers could resolve the discrepancy, but so far, no such revision has convincingly closed the gap. Another line of thought suggests that the lithium was created as predicted, but was later processed away inside the very ancient stars we use as cosmic time capsules. These old stars might have internal mixing processes that slowly drag surface lithium down into hotter interior regions where it is transformed, effectively obscuring the primordial signal. Yet, detailed stellar models have struggled to demonstrate that this process was both universal and efficient enough to account for the full threefold difference we see across many different stars. The most exciting solutions, however, reach for entirely new physics. Could exotic particles from the early universe, like certain types of supersymmetric particles, have altered the balance of nuclear reactions during nucleosynthesis? Their presence could have changed the density or temperature of the cosmos in those first few minutes, tweaking the conditions just enough to produce less lithium from the very beginning. Or perhaps our assumption of a perfectly smooth, standard expansion during that epoch is wrong, and a brief, early period of non-standard cosmology modified the nuclear chain. The lithium problem is a beautiful example of how a small, persistent anomaly can connect the vastly large to the incredibly small. It ties the grand narrative of cosmic origins directly to the intricate details of nuclear physics and the search for particles beyond the standard model. This missing lithium is more than a minor accounting error. It is a faint but persistent signal from the universe's first moments, a whisper that our story of creation, for all its successes, may still be missing a crucial page. Our own galaxy is not drifting through space at random. We are part of a vast, silent river, a cosmic flow carrying thousands of galaxies toward a single, unseen destination. This is the mystery of the Great Attractor, a gravitational anomaly so powerful it pulls on our entire local universe from a region of space shrouded behind the dense star fields of our own Milky Way. In the direction of the Centaurus and Norma constellations, something with the mass of tens of thousands of galaxies is exerting its influence, a force that far exceeds the pull of all the visible matter we can detect in that part of the sky. The sheer scale of this motion reveals a profound truth about the cosmos. The universe is not a uniformly expanding balloon with galaxies sprinkled evenly throughout. On the grandest scales, it possesses an architecture, a cosmic geography of immense gravitational watersheds. The Great Attractor is one of these titanic features, a gravitational basin into which our galactic neighborhood is steadily moving. For a long time, its core remained hidden from our optical telescopes, lying directly behind the obscuring dust and stars of the Milky Way's central bulge, a zone astronomers call the zone of avoidance. It was like trying to see a distant mountain range through a dense, permanent fog. But we have learned to see in other ways. Infrared and radio telescopes, which can peer through the cosmic dust, have pierced this veil, revealing a staggering concentration of mass. They have identified enormous clusters of galaxies, like the Norma cluster, congregating in this zone, their collective gravity beginning to explain the immense pull we feel. Yet, even these vast assemblies of visible galaxies do not fully account for the observed flow. The dominant source of the attraction is almost certainly a colossal halo of dark matter, an unseen skeleton around which the visible structures have assembled. This dark matter web guides the motion of galaxies, creating these immense rivers in the cosmos. The existence of such a large-scale flow challenges the assumption that the universe is perfectly smooth on its largest scales. Instead, it paints a picture of a cosmos still settling, still flowing along the gentle slopes of gravity from the initial, tiny density fluctuations imprinted in the Big Bang. By mapping these motions, we are not just charting our own galactic journey, we are tracing the invisible distribution of the universe's dominant mass. The Great Attractor is a single, powerful clue in a much larger investigation, helping us to draw the first true maps of the dark matter cosmos that holds everything together. While we map the invisible flows of dark matter, we occasionally capture a signal so striking it seems to speak directly to us. On a quiet Ohio evening in August 1977, a volunteer astronomer named Jerry Amon was reviewing data from the Big Ear radio telescope. His eyes locked onto a string of alphanumeric code so extraordinary that he circled it on the printout and wrote a single, powerful word in the margin: "Wow." The signal had lasted for 72 seconds, a sharp, intense burst of radio waves that was both narrowband and focused, precisely the kind of signature scientists predicted an intelligent, artificial transmission from space would produce. It came from a region near the constellation Sagittarius, and then, just as suddenly as it appeared, it vanished. In the decades since, despite countless searches targeting the same patch of sky, the signal has never been heard again. This fleeting event, the WOW signal, stands as one of the most tantalizing and enduring mysteries in the search for cosmic company. The most probable explanations point to natural, if unusual, astrophysical events. Perhaps it was the reflection of a human-made satellite off a piece of space debris, or the radio emission from a passing comet that was not yet known to astronomers at the time. Yet each of these proposals has faced challenges, leaving the signal without a definitive, universally accepted natural source. This very lack of closure is what gives the WOW signal its profound weight. It represents a moment where the cosmos presented us with a puzzle that our current catalog of phenomena could not instantly solve. It forces us to confront the limits of our classification systems, challenging our ability to distinguish between a rare natural event and a deliberate cosmic greeting. That 72-second burst continues to inspire radio astronomers to maintain their patient watch, scanning the skies for other transient events that defy easy explanation. It is a humbling reminder that the universe is capable of producing surprises that do not fit neatly into our existing frameworks, pushing us to expand our imagination about what might be possible in the vast and varied tapestry of cosmic phenomena. Our own planet holds a cosmic secret resting deep within its most ancient rocks. Billions of years ago, our sun was a much younger and dimmer star, shining with only about 70% of its current warmth. By the straightforward logic of climate physics, that weaker sunlight should have turned the entire Earth into a global snowball, a frozen world where oceans were solid ice from pole to pole. Yet the geological record tells a completely different story. We find clear evidence in the oldest sedimentary rocks and fossilized microbial mats that Earth had vast liquid oceans and was teeming with early life. This glaring contradiction is the faint young sun paradox, a puzzle that asks how our planet remained so hospitable when the primary source of its heat was so much weaker. The most compelling answer points to a powerful planetary blanket. Earth's early atmosphere must have been rich in potent greenhouse gases like carbon dioxide and methane, creating an insulating layer thick enough to trap the sun's faint warmth and keep the global temperature above freezing. The challenge lies in the numbers. Climate models struggle to create the necessary heating with carbon dioxide alone without requiring levels that would leave other, contradictory signatures in the ancient rock record. This has led scientists to consider a more complex cocktail of influences. Perhaps volcanic activity provided significant geothermal heat from below, warming the oceans from the planet's own internal fires. Maybe the young Earth was simply darker, with less reflective land surfaces and no bright ice caps to bounce sunlight back into space, allowing it to absorb more of the sun's precious energy. The paradox does not end with our own world. As we discover thousands of exoplanets orbiting other stars, this same question becomes fundamental to assessing their potential for life. A planet positioned perfectly in a star's habitable zone today might have been an ice world in the past, or a future version of its star could render it a scorching desert. Understanding how a planet's atmosphere and geology can compensate for a changing star is the key to interpreting which distant worlds might truly be alive. Resolving this ancient climate mystery is more than an academic exercise. It is about deciphering the delicate balance that allowed life to gain its first foothold and persist through cosmic time, a balance we are only beginning to understand. The serene spiral of a galaxy is a cosmic dance that should not last. According to our most advanced simulations, the elegant disk of stars we see should be a fleeting structure. Within the immense, invisible halo of dark matter that anchors it, the visible galaxy is like a ship tethered to a drifting iceberg by a long, fraying rope. Random gravitational nudges from passing clusters and the constant churn of the halo itself should gradually transfer energy to the stellar disk, causing it to wobble, thicken, and eventually lose its beautiful, flat form over a few billion years. This is the tethered galaxy problem, a deep instability written into the code of our virtual universes. Yet when we look out at real galaxies, we find ancient disks that have maintained their pristine shape for over 10 billion years. They are not shaking apart. Something is providing a remarkable stability, a hidden hand that keeps the cosmic dance in perfect time. The search for this stabilizing force leads us to two profound possibilities, each challenging a different pillar of our understanding. The first points to the dramatic power of the stars themselves. When massive stars end their lives in supernova explosions, they do not simply vanish. They drive colossal winds of gas and energy that push against the surrounding dark matter, effectively stirring the invisible halo and smoothing out its chaotic motions. On an even grander scale, the supermassive black hole at a galaxy's heart, when it feeds, becomes an active galactic nucleus, shooting out jets of radiation and matter with enough force to heat the entire dark matter environment. This constant feedback, a dialogue between the visible and the unseen, may act as a gravitational gyroscope, keeping the stellar disk steady and thin. The second possibility is even more radical. It suggests that dark matter is not entirely dark to itself. What if dark matter particles can interact with each other through some unknown force, not just through gravity? This self-interacting dark matter would behave less like a swarm of silent, passing ghosts and more like a vast, diffuse fluid. Collisions between particles would allow the halo to dissipate energy, preventing the build-up of the random motions that threaten to destabilize the galactic disk. This single idea bridges the immense scale of galaxy evolution with the infinitesimal world of particle physics, implying that the universe's dominant matter might have a rich, hidden physics of its own. The tethered galaxy problem is a quiet crisis in our simulations, a reminder that a stable universe is not a given. It is actively maintained by a complex interplay of forces we are only beginning to map, where the brilliant fury of stars and the secret nature of the unseen together write the rules for cosmic architecture. Our own galactic neighborhood rests inside a cosmic emptiness of staggering proportions. Recent maps of the local universe reveal that the Milky Way is not in an average region of space, but lies at the heart of an immense bubble known as the KBC Void. This is a spherical region roughly 2 billion light-years across, a volume of space about 7 times larger than the average cosmic void, and it is strikingly sparse. Within this vast expanse, the density of galaxies, clusters, and even dark matter is significantly lower than the cosmic average. We are living in a local underdensity, a grand cosmic desert with our galaxy as one of its few oases. This discovery directly confronts a foundational assumption of modern cosmology, the cosmological principle. This principle states that on sufficiently large scales, the universe should look the same in every direction and from every location, a homogeneous and isotropic cosmos without a center or an edge. The sheer size of the KBC Void, however, pushes the definition of a sufficiently large scale to its breaking point. If our entire observable window is inside one of the largest voids in existence, then we cannot assume our local measurements are representative of the universe as a whole. This realization sends a ripple through our understanding of cosmic expansion. The Hubble constant, the rate at which the universe is expanding, is measured by observing how fast nearby galaxies are moving away from us. But if we are sitting in an underdense region, the local gravitational landscape is unusual. The relative lack of surrounding mass means there is less gravity pulling back on the expansion in our immediate vicinity. As a result, space within our void could be expanding slightly faster than the global average. This means our local measurement of the Hubble constant might be artificially high, potentially explaining part of the stubborn tension with the value derived from the early universe. The void could be acting as a local amplifier, making the cosmos seem to be expanding more quickly from our particular vantage point. The implications extend even further. Some scientists have proposed that the apparent acceleration driven by dark energy could be, at least in part, a mirage created by our position inside this vast emptiness. As light from distant supernova travels through the underdense void, its journey is subtly different than through a universe of average density, potentially mimicking the signature of an accelerating cosmos. Could a cosmic coincidence of location be influencing one of the most profound discoveries in modern physics? The debate now centers on whether the KBC Void is a legitimate challenge to the Standard Model or simply a rare statistical fluctuation. In a universe as vast as our own, enormous voids and dense filaments are expected to form through gravity, and we might just happen to live in one of the largest empty regions. To settle this, astronomers are undertaking ever more precise galaxy surveys, mapping the three-dimensional distribution of millions of galaxies to see if our local void is truly unique or if similar structures are common. The answer will determine whether we need to recalibrate our cosmic maps, or if we have stumbled upon a clue that the universe's largest structures hold secrets about gravity and expansion that we are only beginning to perceive. Sometimes the most alluring cosmic puzzles are not found in deep space, but engineered within a laboratory. The story of the EmDrive began as a whisper of technological revolution, a small, sealed chamber shaped like a metal cone that, when filled with bouncing microwaves, appeared to produce a tiny but persistent push. This was not conventional rocketry. There was no fiery exhaust expelled backward to create forward momentum. It seemed to generate thrust from nothing, a modern-day equivalent of pulling oneself up by the bootstraps. The appeal was immediate and powerful. A spacecraft equipped with such an engine could, in theory, accelerate continuously without needing to carry vast reserves of heavy fuel, opening the solar system to human exploration in ways we can only dream of. The reported thrust was minuscule, a gentle pressure less than the weight of a single snowflake resting on your hand. But in the frictionless environment of space, such a force, if real and sustained, could build to incredible speeds over time. This promise captured the public imagination, fueling visions of a new age of space travel. Yet this very promise placed the EmDrive on a direct collision course with one of physics' most sacred principles, the conservation of momentum. For every action, there must be an equal and opposite reaction. A car pushes against the road, a rocket pushes against its own exhaust. The EmDrive, enclosed and emitting nothing, appeared to have nothing to push against. It suggested that we could create motion without an equal and opposing motion somewhere else, a fundamental rewrite of the rules that govern how objects move through the cosmos. The scientific community responded with deep skepticism, as this was not a minor puzzle but a challenge to the foundational logic of physics itself. Rigorous investigative teams began their own tests, attempting to replicate the tantalizing results. What they discovered was a masterclass in experimental subtlety. The tiny thrust signals were almost perfectly mimicked by more mundane, overlooked forces. When the device was powered, it heated up, and this thermal expansion could cause tiny shifts that were mistaken for thrust. The powerful electromagnetic fields inside the chamber could also interact with the Earth's own magnetic field, or even with the experimental wiring and support structures, creating false positive readings. One by one, through painstakingly controlled experiments, these alternative explanations chipped away at the revolutionary claim. The scientific consensus today is that the EmDrive does not work as proposed. Its apparent thrust an artifact of measurement error rather than a new physics. Yet the story holds a profound lesson about how science navigates extraordinary claims. The process of rigorous peer review and reproducible experimentation acted as a filter, separating a captivating idea from physical reality. This case underscores the robustness of our current theoretical frameworks, which have been tested and verified across the universe, from the orbit of Mercury to the bending of light around distant galaxies. While the EmDrive itself may be a technological dead end, its legacy lives on in the renewed curiosity it sparked. It reminds us that the desire to find a loophole in the cosmos is a powerful driver of innovation, pushing engineers and physicists to conceive of even more exotic but physically possible propulsion concepts. The true value was not in the device, but in the conversation it started, a conversation that continues to ask what it would truly take to rewrite the rules of motion and carry humanity to the stars. The universe's accounting system has a major discrepancy, and this time it involves the very stuff we are made of. We have mapped the dark matter and puzzled over dark energy, but there is another mystery hiding in plain sight, the missing baryon problem. Baryons are the particles that constitute all the atoms and molecules of the visible world, everything from stars and planets to our own bodies. According to the precise calculations from the Big Bang, We know exactly how much of this normal matter should have been created in the universe's first moments. Yet when we add up everything we can see today, all the glowing stars, swirling gas clouds, and dusty planets, we come up short. The observable matter accounts for only about half of what our cosmic recipe book insists should be there. It is as if you carefully budgeted for a grand project, purchased all the materials, and then discovered that half of your supplies had simply vanished from the warehouse without a trace. So where did it all go? The leading suspect is not some exotic particle, but ordinary matter hiding in an elusive state. Scientists call it the warm-hot intergalactic medium, or WIM. Picture this as a cosmic fog, a vast web of incredibly diffuse gas that fills the spaces between galaxies. This gas is not cold and dark. It is heated to temperatures between 100,000 and 10 million degrees, so hot that it does not glow in visible light. Instead, it emits a faint whisper of X-ray radiation, a signal that is incredibly difficult to distinguish from the background noise of the universe. For a long time, this intergalactic reservoir remained almost entirely invisible to our telescopes, but we are learning to see in new ways. Space-based X-ray observatories are now tuned to detect the subtle spectral signatures of highly ionized oxygen and other elements within this faint haze. Another technique uses the cosmic microwave background itself as a backlight. As this ancient light travels through the universe to reach us, it passes through these vast filaments of hot gas. The WIM slightly distorts the microwave background spectrum, leaving a unique imprint, like a fingerprint on a window pane. These observations are gradually confirming that the missing baryons are indeed there, woven into the cosmic web. The challenge is that this gas is so incredibly spread out. A single cubic meter of this intergalactic medium might contain only a few atoms, a vacuum far emptier than anything we can create in a laboratory on Earth. But when you add up the sheer volume of space between galaxies, that sparse fog accumulates into a staggering amount of mass, potentially solving the missing baryon puzzle. This hunt is about more than just balancing a cosmic ledger. It is crucial for validating our entire story of the Big Bang. If we cannot find the normal matter that our models insist must exist, it would mean we have profoundly misunderstood the universe's earliest moments. Furthermore, understanding this cycle of matter is key to grasping the life story of galaxies. Galaxies are not isolated islands. They are constantly exchanging material with this surrounding medium, accreting fresh gas to form new stars and losing material through powerful winds. The warm-hot intergalactic medium is the ultimate reservoir, the background ocean that governs the growth and evolution of the cosmic structures we see. Resolving this anomaly reminds us that the universe's greatest secrets are not always found in the utterly unknown, but can be concealed within the ordinary, waiting for our vision to become sharp enough to see what has been there all along. Even the light from ancient galaxies carries a subtle test of cosmic reality. One of the most elegant checks on the expansion of the universe is known as the Tolman surface brightness test. It asks a beautifully simple question. If we look at a galaxy very far away and therefore seen in the distant past, how does its inherent glow, its surface brightness, compare to a similar galaxy nearby? In a static universe, or one described by some alternative theories, that intrinsic brightness would remain constant regardless of distance. But in an expanding universe, something more profound happens. The stretching of space itself does more than just redshift the light, shifting its color toward the red. It also dilutes the energy of the photons and stretches the apparent area of the galaxy on the sky. This double effect causes the surface brightness of a galaxy to fade dramatically with its redshift. It is like watching a distant street lamp on a foggy night. its light seeming to dissolve into the gloom not just because it is far, but because the very air seems to be pulling its glow apart. This dimming is a direct prediction of the expansion we associate with the Big Bang. For decades, a competing idea known as the tired light hypothesis proposed a different explanation. It suggested that light simply loses energy during its long journey across the cosmos, perhaps through some unknown interaction with the fabric of space, growing redder and dimmer without any expansion at all. The Tolman test provides a clear way to distinguish between these two pictures. If the universe is truly expanding, the surface brightness should drop in a very specific way with distance, a signature that is distinct from simple energy loss. The vast majority of observations, especially of giant elliptical galaxies which are excellent standard candles, strongly support the expanding universe model. The dimming we see matches the predictions of cosmic expansion, not a tired light scenario. Yet, science thrives on nuance. Some studies have noted minor discrepancies, small deviations from the perfect theoretical curve. Could these be hints of something unexpected? The immediate suspects are astrophysical in nature. Perhaps distant galaxies are intrinsically different from their local counterparts, their stars younger and brighter, subtly altering the measurement. Or maybe cosmic dust floating between us and them is providing an extra layer of dimming that mimics a tired light effect. Researchers meticulously account for these evolutionary and environmental factors, and even when they do, the core conclusion holds firm. The expansion of the universe remains the most robust explanation for the data we have. The enduring value of the Tolman test is not that it overturned our cosmology, but that it reinforces it through relentless scrutiny. It exemplifies the scientific process at its best, where even the smallest anomaly is investigated, not as a threat, but as an opportunity to secure our understanding. This continuous refinement of cosmic measurements ensures that our map of reality is drawn not in permanent ink, but in pencil, always ready to be sharpened by the next clear observation from the depths of space. Etched into the oldest light in the universe is a chill that defies easy explanation. On the detailed maps of the cosmic microwave background, one region stands out as profoundly cold, a vast patch of sky where the temperature of the primordial glow is significantly lower than the surrounding average. This is the CMB cold spot, an anomaly so large and so pronounced that it has captivated and confounded cosmologists since its discovery. It is a grand cosmic feature, a subtle mark on the otherwise remarkably smooth face of the infant cosmos. The simplest explanation is that it is just a statistical fluke, a rare random fluctuation in the same way that flipping a coin 1 billion times might, by sheer chance, produce a long string of all heads. Yet the sheer size and depth of this cold region make that simple answer feel increasingly unsatisfying. The probability of such an extreme fluctuation occurring by random chance is extraordinarily low, prompting scientists to ask if the universe is trying to tell us something. Could this cold spot be a fossil, a relic from the universe's earliest chapters, pointing to a physical process beyond our standard model? One of the most compelling exotic ideas involves a cosmic texture. Imagine the early universe cooling from an indescribably hot, symmetrical state, like water freezing into ice. As it cooled, the very fabric of spacetime might have undergone a phase transition, and in that process, it could have developed unique features, gentle kinks and tangles in the underlying fields. A cosmic texture would be one such feature, a knot of concentrated energy that, if it shifted, would leave a distinct imprint on the cosmos, a signature precisely like a large, cold spot in the microwave background. It would be a memory from the cosmos's first moments. Another possibility is that the cold spot is not a feature of the primordial universe at all, but a later effect created by a vast, mostly empty region of space, a supervoid lying between us and the CMB. As light from the cosmic microwave background travels through such a void, it would lose a tiny amount of energy climbing out of the underdense region's gravitational well, a process known as the integrated Sachs-Wolf effect. This would slightly redshift the light, making that patch of the sky appear colder. The challenge is one of scale. To produce the observed cold spot, this void would need to be unimaginably large, one of the biggest structures in the entire observable universe. Astronomers have searched for such a supervoid, and while some underdense regions have been identified in that direction, none have been conclusively shown to be vast enough or empty enough to fully account for the profound chill. This leaves the mystery wonderfully open. The cold spot represents a beautiful tension at the heart of modern cosmology, where a single anomaly in our most precise data set drives theoretical innovation. It forces us to consider models that extend beyond our comfortable standard paradigm, to imagine a more complex and textured cosmic history. Whether it is ultimately confirmed as a rare fluctuation, a cosmic texture, or something else entirely, its enduring presence on our maps is a powerful reminder. The universe is under no obligation to be simple, and its deepest secrets are often hidden within its faintest irregularities. The largest structures in the universe are spinning, and we are only just beginning to understand why. Galaxy clusters, these colossal metropolises of thousands of galaxies bound together by gravity, do not merely drift through the void. They exhibit a slow, coherent rotation, a shared motion that presents a profound challenge to our models of cosmic construction. According to the standard hierarchical picture, these clusters should form gradually, with smaller groups of galaxies merging together over billions of years. In this chaotic, cosmic dance of collisions and accretions, the cluster as a whole is expected to acquire a small amount of net spin, a faint angular momentum imparted by the gravitational tides from surrounding large-scale structures. Yet when astronomers measure the rotational velocities within these immense systems, they sometimes find a signal that is stronger and more organized than the simulations predict. It is as if you stirred a cup of coffee with 1,000 random flicks of your wrist, expecting a turbulent swirl, but instead found the entire liquid turning with the smooth, deliberate spin of a carousel. This orderly motion on such a grand scale is difficult to generate through the messy process of hierarchical merging alone. The rotation we observe suggests that the process of building the universe's largest structures is far more nuanced than we thought. The accretion of matter onto these clusters and the subsequent transfer of its inherent spin must be a highly efficient and coordinated process. Perhaps the vast, invisible halos of dark matter that anchor these clusters are not perfectly smooth, but possess their own complex substructure and dynamics, guiding the incoming galaxies into a shared rotational flow. Or maybe magnetic fields, which thread through the incredibly hot gas that fills the space between cluster galaxies, play a more significant role than we realized, acting as a kind of cosmic glue that helps transmit angular momentum across vast distances. Resolving this discrepancy is not just about fixing a number in a simulation. It forces us to look more deeply at the fundamental interplay between the dark matter scaffolding of the universe and the ordinary, baryonic matter we can see. The rotation of a galaxy cluster is a fossil record of its entire assembly history, a single measurement that encodes billions of years of gravitational interactions. By refining our simulations with more realistic physics and comparing them to ever more precise observations, we are essentially learning to read this cosmic chronicle. Understanding how these titanic systems acquired their spin is a crucial step in mapping the full life story of the cosmos, from the faintest ripple in the early universe to the grand, rotating architecture we see today. Even the quiet hum of deep space holds its own peculiar music. Across the galaxy, in the dark clouds between the stars, astronomers detected a faint but persistent microwave signal that simply did not belong. It was an anomalous microwave emission, a ghostly whisper of radiation that could not be explained by any of the usual suspects, not the frenetic spiraling of electrons in magnetic fields, nor the brief encounters of free-floating particles. For years, this signal was a spectral presence on their charts, a cosmic static with no clear source. The resolution to this mystery did not come from rewriting the laws of physics, but from looking more closely at the tiny components of cosmic dust. The answer, it turns out, is dust itself, but not the inert, floating specks we might imagine. These are nanoparticles, tiny carbon-based molecules known as polycyclic aromatic hydrocarbons, spinning at incredible speeds, billions of times per second. As these minuscule grains rotate, they carry an uneven distribution of electrical charge, and this spinning electric dipole acts like a microscopic radio transmitter, emitting a faint but detectable signal in the microwave band. This phenomenon, aptly named spinning dust, revealed an entire population of previously overlooked actors in the interstellar theater. The discovery forced a major revision of our models of the interstellar medium. We had to accept that this cosmic void is not truly empty, but a complex ecosystem filled with a diverse family of dust grains, each with its own size, composition, and behavior. The spinning nanoparticles operate in a realm where solid-state physics and astrophysics collide, a domain where the quantum properties of a molecule can have consequences on a galactic scale. This anomaly did not point to a flaw in our core theories, but to a gap in our cosmic inventory. It showed us that the darkness between the stars is alive with subtle processes, a reminder that sometimes the universe's quietest signals can lead to the most resonant discoveries about the intricate material world that builds everything we see. Our journey through the cosmos uncovers a reality far more wondrous and enigmatic than any fiction. The laws of physics we once considered absolute are not so much broken as they are revealed to be incomplete, mere local ordinances in a universe of boundless possibility. Each anomaly, from the steady influence of dark energy to the mysterious heart of a black hole, serves as a gentle reminder that our understanding is still in its early stages. These are not failures of science, but its ultimate purpose, signposts pointing toward a deeper truth just beyond our current reach. They encourage us to think bigger, to question more deeply, and to refine our vision of the cosmic fabric. This ongoing pursuit drives the very engine of discovery, pushing the development of ever more sensitive telescopes and inspiring bold new theoretical frameworks. The goal is a grand synthesis, a single theory elegant enough to embrace both the subtle connections of the quantum world and the vast geometric curves of spacetime. The greatest chapters of this story are still being written. Your own sense of wonder is a vital part of this ongoing adventure. If this exploration into the unknown has sparked your curiosity, consider subscribing for more journeys to the edge of understanding. We would love to hear which cosmic mystery captivates you the most, so share your thoughts in the comments below.